Jaqueline is here. Where are you? Yeah,
I
okay.
am here.
If you want, you can share your slide. And I was okay. I would like to say some words about Jaqueline. Okay, if Jaqueline try to show her slides. Okay, okay. So I wrote this some few words. So today I have the great honor and the difficult task, of introducing in such a few minutes my young friend Jaqueline Godoy Mesquita, a professor at the University of Brasilia. First of all, I would like to thank Jaqueline for having accepted our invitation to deliver this lecture in our seminar. Thank you very much. Jaqueline got her PhD in 2012 at the University of São Paulo. Since then, she has had a successful career, both for her scientific contributions to the mathematics, in the area of the mathematical analysis, as well in this dissemination of science and her struggle for gender equality in science. Jaqueline has published numerous papers, has mentored students, and she has delivered many lectures as an invited speaker. However, I would like to highlight here only some of the distinctions she has received in recent years. Um, in, in 2012, she has won the International Bernard Albach Prize for Students, awarded by the International Society of Differential Equation. In 2018, she was elected Young Affiliated Member of the World Academy of Science and affiliated member of the Brazilian Academy of Science. And finally, in 2019, she won the prize for Women in Sciences, awarded by L'Oréal, UNESCO, and Brazilian Academy of Science at the category of mathematics. I could go on talking about Jaqueline's achievements, but I will now let you hear the lecture she came to present to us. So, Jaqueline, it's up to you now. Thank you very much for being here. I'm very happy.
Thank you very much, Sandra, for this nice introduction, for this kind introduction. I'm really glad to be here, and also I'm glad for the invitation. So thank you very much, Sandra, Juan, for this invitation. It's a great pleasure to me to be here and to be able to talk a little about my work. So thank you very much. And also, I'm so glad to see many friends here today. So thank you very much for the audience, for the presence. So today I'll talk about linearized instability for neutral functional differential equations with state-dependent delays. So the outline of my talk, I divided it in three parts. So I will start with some preliminaries and motivation, since I don't know if everybody here is familiar with delay equations. So I will bring some motivation to investigate these types of equations. Then I will go to this specific problem, that's the linearized instability principle for neutral functional differential equations with state-dependent delays. And then I will talk about open and developing problems. So I will start with some motivation about delay equations. So when we try to come back in history and try to understand when it started to be investigated, these types of equations, we have this citation from Vitor Volterra, which says, in all biological phenomena, it's necessary to examine not only immediate actions, but also those depending on the past, that is, on the changes which the species have undergone. These actions were first called hereditary actions, but this name was not well chosen. It was found preferable to use the term historical actions or actions belonging to memory. So in that moment, Vito Volterra brings the importance to considering delay equations in order to describe more precisely the biological phenomenon. Then later, we have that Picard. He was a plenary speaker at ICM in 1908, and in his plenary talk, he also mentioned about the importance of to consider delay equations in order to describe better many types of phenomena. And here, only to bring some view how it could be some interpretation of the delay, I bring here a population model. I will be very superficial, not technical, only to bring a motivation to investigate these types of equations. So here we have the logistic equation that's very famous, and I'm sure that everybody here have heard about these equations. And this equation is very important to describe the population. And then later we have Hudson, was one of the first to start to think that, okay, that's nice, this type of model, but the process of reproduction is not instantaneous. We know that when the baby born, it's not possible to reproduce. We know that there is a time in between the birth and to enter in the maturation process. And this time can be described using these delays. And then Hudson was one of the first to reformulate the logistic equations and put here this delay. So here we have this delay term in that equation. And then probably you are seeing that and think, okay, it will not change very much. You only add some tau here that's constant, and it will not change a lot the dynamics or the behavior of the solution, but it changes a lot. So if we see, here is the solution of the logistic equation, and this is the solution of Hudson equation. So we can see that it has this oscillatory behavior. So it changes a lot when you put that delay. So that's why it's so important to consider it in the equation. And there are a lot of examples of populations which oscillate as described by the Hudson equation. However, although that was a very nice idea to put this delay here, if you have a look very carefully for this Hudson equation, making a distributive here, you will see that he put the delay term in a negative part, which means that it's in the death rate, not in the birth rate as he would like to put. So realizing that, we had the contributions of these mathematicians, so Alexander Nilsson, and also other scientists, Perry, Smalt, and Coutinho, and they improved the model and put the delay in the right part. So here now, the delay is in the right part and with the correct interpretation. So here is the Blow-Phi equation. It's well known like this because they studied a lot the Blow-Phi population using this type of model. And so here you can see, for example, when we have the tau equal 2, we have this behavior, tau equals 6, we have this other type of behavior, and so on. But here, if you see, we considered the delay constant. However, many authors later found out that the delay constant in that type of problem is not so realistic. So it's important to considering a state-dependent delay. So in these three authors, they realized that the total of population can change depending other variables such as amount of food. So here we can see that they mentioned that it was observed that for Antarctic whale and seal populations, the length of time to maturity is a function of the amount of food, mostly krill, available. So, and they do some analysis talking about that this time in between the birth and to enter in the maturation process, it will depend on other factors, such as the amount of food. And then they reformulate the model, and they bring that formulation using here, not a constant delay, but a delay which depends on the state. So state-dependent delay model. So if you see, this is a type of formulation of the other model. If you do some change of variables, you can arrive in the other one. However, here the main difference is about this state-dependent delay. And they published this in this paper. So here you can see how it looks like the behavior of the solution when we considering this state-dependent delay in this interval. And also, if we want to do some a comparison with constant delays, here in the case constant delay equal 14, we can see that here in that specific case, it's not so different. So we can see that it's almost the same, but which changed here is the size of these oscillations. However, depending on the model that you are dealing, you can have much more differences when you're considering constant delays and state-dependent delays. So because of that, we need to be careful when we deal with both. So that was to bring some motivation to investigate these types of equations, the delay equations, especially the ones with state-dependent delays. And now I will talk about a little more technical about this problem that we investigated, that's the linearized instability principle for neutral functional differential equations with state-dependent delays. So this work was made in collaboration with Professor Bernhard Landweide from Justus Liebig University in Germany. And I will talk a little about the timeline of this problem, why we were so interested about it. So we have that in 2004, Brunovsky, Erdely, and Walter, they decided to investigate some model to study exchange money. And they bring that formulation for that model, and they investigated some properties such as existence and uniqueness, and try to investigate some asymptotic behavior of the solution, but it was not so easy, and they made some conjectures about the asymptotic behavior of the solution. Then later, in 2005 and 2006, Hans Otto Walter, he investigated deeper this model, and he investigated periodicity of solutions and also bifurcation. Then later, Garabi, Kovacs, and Christine, in 2016, they proved some conjecture that they had in this first paper about the asymptotic behavior of the solution. And then in 2012, Stamp was one of the first to try to reformulate this model considering state-dependent delay. So now you can see that the delay here depends on the state. It's not more constant as we had here before. So he was one of the first to deal with that. And of course, it brings much more complications, these state-dependent delays. And then Hans Otto Walter in 2013, realizing that he could improve more the model, he put here this derivative. And now what we have here, when we have the derivative in the part that contains the delay, we have a called neutral functional differential equations. And since the delay depends on the state, we say that with state-dependent delays. So this was the model that Hans Otto Walter brings, and he investigated about that model. So he investigated about existence, uniqueness of solutions, differentiability, continuous dependence, and stability. However, for the instability, we have a big problem when we deal with neutral equations. Because since we have this situation here about the derivative, when we linearize that and we try to investigate the instability, we have some problems about the spectrum. Because in the spectrum, the linearized equation that comes from here, we have infinite eigenvalues. So it's very hard to have some lower estimated for our semigroups. And here brings the most difficult to deal with this problem about instability. But we decided to face this problem, and then in 2019, I spent 1 year in Germany working that specific problem, and we had some results about linearized instability for these types of equations. So we have this problem. That's the problem that Hans-Otto Walter reformulated, that we would like to investigate it, the linearized instability. And our first goal is to rewrite this equation. That form here was made by Hans-Otto Walter, so we took that part ready, that to rewrite this in that form. And also we need that this one satisfies certain conditions, because we would like to use some results that Hans-Otto Walter proved in his paper about existence, uniqueness, differentiability, and so on. We would like that these properties continue valid here in our case. So we also used the same formulation and also this hypothesis in order to ensure that we can continue with these results valid. And only to tell you, because maybe you are seeing this notation and thinking that's a partial derivative here with respect of t. However, it's not. When we deal with functional differential equations, it means that this x of t is a function of theta. So this is a function of theta, and it's given by x of t plus theta, where theta belongs here in that interval. Of course, we can consider including the theta in this unbounded interval, but it's much more complicated. So here, as I mentioned, we would like to rewrite this problem in that way here. So in order to do that, we need these two evaluation maps. So here's the evaluation map that brings this pair to that, to this application of the function. And here we have times the continuous functions, and here we have the restriction of this evaluation map. And using both, we will be able to rewrite in that form here. And of course, with these conditions that I mentioned, that it will be very important to us. So here, if we define our G in such a way involving the evaluation maps and the restriction, and also the projection, here's the projection with respect with the second factor, and here's the projection with respect of the first factor. We have that using this G here, we have that this G will satisfy certain conditions that will show, and using that we can have all the results that were proved by Hans-Otto Walter. So we will deal with this type of problem with that special G. And here's the definition of the solution of that problem. So a continuous differentiable function. It's called a solution here if it satisfies this tree for all t here. And also we have this pair belongs to omega, where omega is an open subset of here. And so here we have the conditions. So the first one is about the continuity of the function g. The second one is about the delay in the neutral terms never vanishes. We use that to mention the following, that here, if you have that phi1 is equal to phi2 for this interval, so it doesn't matter what happened in the interval minus delta until 0, because you have that the g will be the same when you apply it for phi1 or phi2. So you have this equality here. So this, in other words, you can say that the delay in the neutral term never vanishes. So you always will be with a neutral equation. Here for our model, that's okay, that's a great condition. But of course, if you have a model that you need some talk between the particles, the speed, and so on. So in that case, you could have this a neutral term, it's vanished, and in that case, we're not interesting to have this type of condition. But in our case, in our model, we do not need that the neutral terms vanish. So that's okay, and it will be very important to us to have this type of condition. So here also we need some local estimates of our function g. And also here we need these conditions about the linear extension of the derivative, because we will need to construct some manifolds. So here we have that every derivative has a linear extension. So here, the derivative is defined in that domain, and then we can extend it using this one here. So we have the linear extension. And using that property, we have that D set given by all the functions here, mu1 intersected with C2, such that satisfies this equality here, is a continuously differentiable submanifolds of the Banach space C2. And then we are here also considering this norm. Also here we have this other assumption about also estimated, and here about the upper semi-continuity of the function. And also we have this other assumption again about some estimated. I will not enter deeper in the assumptions since they are too technical, but using these assumptions we can ensure, as I mentioned, about the existence, uniqueness of solutions, also properties of differentiability, that will be very important to prove our results. And also here we have that these closed subsets, that's a closed subset of our manifold. When we construct like that, we have that this one is invariant, because we have that our manifold is not invariant, but this one, that the closed subset is invariant, is a subset invariant. So using that, that was proved by Hanzotto-Walter, that if you start here in this closed subset, you will continue that when you go forward with this T. So it's invariant. So you start there and you continue that. So this set has that property that will be very important to us here. And because here we do not have that with our manifold. So because of that, we need to construct these closed subsets. So now we go to the part, the most important part, that's to prove that 0 is unstable. And in order to prove that, we will use the invariance of cone. So here we will start with some general assumptions. So with an abstract framework, and then we will go to our concrete framework. So here, the first hypothesis is about the decomposition of the space in the unstable part and the stable part, and also that we have this inequality here in the unstable part and this one in the stable part. Also here it's about the semi-flow, so we have this is a semi-flow and satisfies the properties of the semi-flow. And also we define this function R of t as this difference between these two functions here for x here next and t belonging here, and assuming that there exists T1 bigger than 0, such that for every epsilon bigger than 0, there exists delta for all x here in that intersection, such that T1 belongs here, and we have this inequality. So these are our assumptions, and with that, and of course here only to mention that since we don't want to use all the time in this K1 in our accounts, we will use here an equivalent norm that we've denoted by this. And with this equivalent norm, we will be considering our Q equal 1. So we have these inequalities here. And also this norm will be the maximum between the unstable part and the stable part. So we have also this. And so here for C, in that interval, we define our cone. So our cone will be all the elements in E, such that V is in the stable part and U is in the unstable part, and satisfies this inequality here. And then we have our result about the local cone invariance and expansion. So let's see here, and T1 bigger than 0, as in our hypothesis A3. And then if we take our Q given by this, so we can see by the definition that our Q is bigger than 1, since we are assuming that beta is bigger than 0. Then under that hypothesis, there exists delta bigger than 0, such that if we start in the cone here, we will continue in the cone in the T1 map. So here I apply the T1 map, and I am still in the cone. And more than that, I have an expansion of the unstable part. So here, the unstable part, there is an expansion because this Q is bigger than 1. So that's our lemma. That's the local cone invariance and the expansion. So here is a sketch of the proof. So we will take this epsilon as the minimum between these two values here, and we will take our delta as in the hypothesis A3 for this norm, and then we will use that fact to have some estimated here. So here first we will use that equality that we had before about this R. We had that R is given by phi minus S of 2, and then using that we have that we can rewrite it in that equality. And here we are only organizing things. And now we're using the estimated, we use here the inequality, the triangular inequality for the other side, and also the estimated for the semigroup in the unstable part here. And here we are using the assumption A3. So using then, we have this inequality here. And then here we are using the properties of our cone, and then we have this other estimate. So we have this estimated here for the projection applied here for the T1 map. And now doing the same, but now about the stable part, again, we can rewrite it in this way here using the definition of R that we gave in the assumption A3. And then here organizing, we have that. And here we use the triangular inequality and the upper estimate of the semigroup for this first part here. And here again, we use the properties of the projection and also the assumption A3 here. So we have that. And then here again, using the properties of the projection, so we have this other inequality here. So we have that this one is smaller or equal this. And now, using the definition of this norm that we saw that it's the maximum of the stable part and the unstable part, but we saw that the stable part is smaller or equal this estimated. So we have that this one is smaller or equal this maximum here. So we will considering these two possibilities. Or this maximum is equal this, or this maximum is equal this, and we will try to prove the invariance of the cone in both cases. So first we will start assuming that the maximum here is this one here. So it's given by this. So this is the maximum. And then we have that since this is the maximum and this is smaller or equal this maximum, so we know that this one is bigger or equal this from that inequality. But we are assuming that C is smaller or equal 1. So this one is bigger or equal C times this norm here. So if we see here, we have that our T1 map belongs to the cone. So we have the invariance of the cone in that case. So now we will assume that this one here is a smaller, this maximum now is given by this here. So now we will use the other possibilities for the maximum. So now using that, we have that this one here is smaller or equal to this from that possibility for the maximum that we're assuming that is this one. So this is smaller or equal to this. And then here we always sum and subtracting the terms of with the C, so we have that. And then now using the definition of epsilon, we have that's smaller or equal this thing here, and then we have that. But this one we showed it before, that is smaller or equal the projection of the unstable parts of the T1 map. So we have this estimated, and then if we have that estimated, which allow us to conclude that the T1 map belongs to the cone. So the cone is invariant, and now we need to show that it's also expands the unstable part. So now, to show that, we will use the choice of epsilon and also the property of to be in the cone and some estimated that we had before, and then we have this first estimated that we showed before about this unstable part of the T1 map. And then here, using the property concerning our cone, the fact that x belongs to the cone, we have this one here that appears with this projection of in the unstable part. And also here, using the definition of the epsilon, the choice that we had before, we also have this other estimated. And then here, if we calculate, we have this here. And this one is exactly our Q. So we have this equality, and then we have this inequality here, and we prove the expansion of our unstable part in the T1 map. So we proved that lemma for the abstract framework. So here, using these spaces, and we can translate for our concrete framework, and then we can pass for our specific case. We need only to show that all data assumptions A1, A2, and A3 are all satisfied. So for the A1 is the most complicated because the things that I mentioned about the spectrum, because we could have infinite eigenvalues, and then it's very hard to have a lower estimate, but we could have some examples in our case that fits in our model to considering these lower estimates. But of course, we cannot have that for any neutral equation. So we need to be careful about this part. But in our case, for our model, that fits okay in some examples that we could find, and that's important for our model. And also we could prove for the others properties. The others are not so difficult. We can have that from the properties that Hans Otto Walter has proved before. So we only needed to use that and do some estimated and then prove that we could have all that conditions satisfied for our specific case. So now we have here one more assumption, because we have here this additional assumption concerning our function g that has that this one has a continuous extension given by this restricted to that set. And here we need that because we want to construct a manifold, because you remember that before that we have this set here that's invariant, but it's not a manifold. And now we need a manifold, and then because of that, in order to show that this one is a manifold, we need this property concerning the second derivative. So using that, we can show that this one is a manifold. That's the intersection of this invariant set and C3. And now, the main idea that we have is the following to prove the instability. So, in order to prove the instability, we will start in the ball with our solution. And our idea is to show that the solution will escape from the ball. And so we have that. We will start in the ball, we will start in the manifold M3, and we will start in the cone. And then we will apply the T1 map. When we apply the T1 map, if we escape from the ball, we finish it. If we do not escape from the ball, so we will apply again, but we need to observe that we will continue in the cone because the cone is invariant, as we showed it before, and we are not longer maybe in the manifold. We don't know if we are here or not, but we know that we are in that invariant subset, that's X, G2 star. So we are in that invariant subset and also in the cone. And then we apply again the T1 map. And if we escape from the ball, we finish it. But if not, we apply again and we apply again. And some moment we need to escape from the ball because we saw that our cone expands the unstable part. So in some moment, our solution will escape from the ball because we will continue in the cone because the cone is invariant. So we apply the T1 map, we are there, and we apply the T1 map and again, and we will still in the cone. In some moments, we need to escape from that ball because of this expansion of the unstable part. And so here it is exactly what I explained about this principle of linearized instability. So we have this assumption, and what we have is that in some moment there exists some Tn that will escape from the ball. So we have that our Tn map will no longer belongs to the ball. And with that, we have the linearized instability principle. So now I would like to mention about some open and developing problems in that area. There are several things to investigate in that area, since it's a very new area, especially this part about neutral functional with state-dependent delays. There are a lot of open problems that would be very interesting to think. So first, I am very interested about this type of equations that's a little more general than neutral functional differential equations, that are the measure neutral functional differential equations with state-dependent delays. So this one, we can encompass many types of equations inside of this class. That's the measure. We can put equations with impulses, equations with the time scales, many different types of equations because of this type of measure equations. And in my case specifically, I am trying to relate these types of equations with a more general class that's called the generalized ODEs, and to try to have some results in that directions, results about existence and uniqueness, stability, results, some more general with under more general conditions. But also about only neutral functional differential equations with state-dependent delays, there are a lot of open problems. For example, the periodic solutions for that problem, for that model that I showed today, are still open. We don't know if there are, I don't know, under which conditions we can have periodic solutions, also about bifurcation. So there are a lot of open questions about this class of equations that are the neutral functional differential equations with state-dependent delay, including this specific model that I showed today. Of course, we can also think about other types of models for neutral functional differential equations with state-dependent delays, and there are a lot of things to think about in that direction. For example, one thing that motivated a lot this area about state-dependent delays were the works from drivers, because driver started to investigate the problem of three bodies in electrodynamics. And he realized that it's very important to consider in delay in that case. And not constant delay, but delay depends on the state, which means state-dependent delays. And in that type of model, he considered such a type of neutral functional differential equations with state-dependent delays. So there are a lot of things to do in that direction, including thinking in new models. So, and also this periodic solution for this specific case, that this model of exchanging money also is an open problem. Also about attractors, the global attractors for neutral functional differential equations with state-dependent delays is a still open problem. We have such a, including for functional differential equations with state-dependent delays, is a still an open problem. So we tried to think about this when I was in Germany, together with Hans Otto Walter and the professor Tomás Caraballo from Spain. And we tried to think how we could have this global, to ensure the existence of global attractors for these types of equations. But for neutral, we started to think, but we decided to start first with the functional differential equations with state-dependent delays, and then try to advance to see if it's possible to generalize for neutral. But even in that case, without the neutral part, it's very hard to deal with this setting, also this framework. So there are a lot of things to think in that direction, and about these types of equations with state-dependent delays. Also, there is a very recent result from Christine that he investigated a model that for example, if you'd like to understand the line of the time of for processing the computer So when you try to describe that in model, you need to consider in delays, because it will, the time for processing will depend on how many things you put your computer to think at the same time. And it is a not constant delay, but a delay which depends on that line. If you put many things to open at the same time and for your computer processing, of course, this delay, this time will be longer. So it's a time, is a state-dependent delay. So the Christine and his co-authors, they made one model very interesting in that direction, which is described by a functional differential equations with state-dependent delays. So there are a lot of things to think in that direction. About some models involving delays, including combining partial differential equations with delay equations. So also it's very interesting to think about that. So thank you very much for your attention. It was my great pleasure to be here. And I'd like to thank you very much for the organizers for the invitation, especially to Sandra.
Okay, thank you, Jaqueline. I think, thank you very much for your great conference. And I think you can move to Portuguese, because I think Professor Laziekan is not here anymore.
Okay.
There is a problem? I don't know, maybe, or no, I don't know. So, we have questions, some questions on chat. If you have some question, please, you can put your questions in the chat. So I'm not seeing. Jaqueline, you spoke. You said at the end of your conference about this mixing of partial differential equation and this functional differential equation. Do you have some example, some model that people could work on it?
Yes. Ok, eu vou falar em português ou em inglês.
Sim,
Não sei.
sim, vamos. Ninguém falou nada, vamos falar.
Em português ou em inglês?
Sim.
Tá.
Pode ser em português, acho. A maioria da plateia também é.
Se
a
quiser,
grande
eu falo
parte
em
em espanhol. Mas tudo bem, podemos falar em português.
Se quiser, eu posso falar em inglês também, preferir. Ok, aí.
Então,
Tá.
em português.
Em português? Então tá.
Pode.
Tá bom. Não, então, com relação a isso, inclusive o Matofu tá aqui, né? E o Paulo Seminário acho que também tá aqui, não sei, eu tinha visto ele antes. A gente tem um trabalho nessa direção, né? A gente tem um artigo que é justamente colocando uma EDP e colocando retardo junto, que é a equação de Lamé, né? Então a gente colocou os dois juntos aí. Foi até uma ideia do Matofu, né, e do Paulo aí, né, de fazer essa, de juntar, né, as duas coisas aí, colocar nesse modelo. E tem até alguns estudos já também nessa direção, tem a Cristina Pinotti, né, que tem alguns trabalhos também que envolvem EDPs e também retardo, então...
Muito bom. Quando a gente mistura essas áreas assim de, né, que está trazendo tão cheio de problemas em aberto, né, que você estava mostrando aí no final, interessante. Aqui a grande maioria aqui, o pessoal de EDP, né? Alguém tem alguma coisa? Estão aqui agradecendo sua palestra, dizendo muito bacana, excelente conferência. Em espanhol, em portunhol. E alguém.
Eu vou fazer uma, Sandra, posso? Para a Jaqueline?
Sim. Claro. Quem está falando? Gilmar?
Tudo bem?
Parabéns. Oi, Gilmar.
Oi, parabéns pela apresentação aí. Então, na parte discreta da EDP funcional, né, neutral, vocês chegaram a fazer algo de transformada de Fourier inversa, ou filtragem, ou coisa nesse sentido?
Não, assim, a gente não fez assim, nada nessa direção. Não sei se tem, né? Se de repente o Matofu conhece alguma coisa nessa direção. Eu não conheço nada, assim, com retardo junto, eu nunca vi, mas eu não sei. Eu não tenho tanta experiência com EDP e retardo juntos, né? Na verdade, o meu primeiro trabalho nessa direção foi com o Matofu e o Paulo, né? Então, assim, eu nunca vi nada assim, mas... Matofu, pode falar, se quiser aí complementar.
Ô, Gilmar, aqui é a Matofu, tudo bem?
Tudo bem.
Então, o que eu tenho visto, assim, mais, assim, modelo discreto, inclusive com uma simulação numérica, é modelo de epidemia, tá? Que tem uma equação de difusão, aí eles colocam retardo, né, para simular algum efeito, e aí fazem a discretização para fazer uma análise numérica. Mas, assim, eu acho que o trabalho da Jaqueline era mais teórica, né, mais qualitativa. Então, talvez seja um outro vertente, né, uma outra vertente.
Legal.
Que
Tá
pode
bom,
se
obrigado.
juntar, né? Que pode se juntar também, né? Essas duas coisas. Achei bacana também ter alguém aí, um pouco de numérico, né? Junto com coisa, vai ficar muito bacana, né?
Sandra, por exemplo.
Pode
Tem
falar,
só antes que eu esqueça, só um minutinho, tem uma pessoa pedindo para falar, é o professor Cortez. Professor Cortez, pode falar, por favor.
Boa tarde. Eu gostei muito os modelos que ele apresentou. Ele apresentou a regressão logística e também, eu acho que eu entendi, era o crescimento periódico dos animais, né, que geralmente estão afetados por vítima predador. Né? É isso que eu entendi nos modelos que ele apresentou. Eu sei que a estabilidade é muito interessante, mas eu gostaria de saber essa estabilidade em que ajuda no problema das predições, né? Que se eu ganho estabilidade, para que realmente? No caso de epidemia seria um caos, né? Mas aí nesse caso eu estou querendo predizir o quê? Isso eu gostaria de saber.
Você disse, assim, nesse modelo que eu mostrei, é um modelo bem simples, né, na verdade, assim, só seria, assim, tá ali meio que uma reformulação da equação logística, né, e a gente colocando ali o retardo. Mas, sim, você pode ter modelos muito mais complicados, né, colocando retardo, na questão, como você falou, da própria, da epidemia. Eu já vi alguns trabalhos, por exemplo, tentando simular a questão da Covid usando retardo. E aí, nesse caso, considerando esse período de incubação, né, como sendo retardo. E aí, justamente, assim, até para você considerar esse retardo constante, tem um certo cuidado, porque o tempo de incubação do vírus, ele não é constante, mas ele varia, né? Então, assim, tem gente que às vezes apresenta os sintomas mais rápido, outros demoram mais, e você demora para isolar essa pessoa que está demonstrando os sintomas. Então, eu já vi alguns modelos bem interessantes usando esses retardos, e aí, de fato, você fica com esse comportamento oscilatório, né? E aí, até o pessoal fala que lembra um pouco das ondas, né, que a gente tem, que é justamente isso, você abrir e fechar, e tendo esse retardo, né, de quando você está se manifestando, e aí fica vindo essas ondas. Mas aí, bom, eu não sei se é algo nessa direção que você queria saber, mas normalmente, quando você coloca esse retardo, você começa a ter esse comportamento, ele forma esse comportamento oscilatório. Aí tem muita gente que estuda controlabilidade, coloca às vezes uma perturbação para poder controlar, né, para poder às vezes é instável a solução, então você pode colocar outros termos para tentar ganhar estabilidade.
Ok, obrigado. Sim, ficou muito claro. Meus parabéns. Também felicitar a Universidade de Brasília. Né? Eu lembro, quando eu estudei lá, né, no ano 72, da promoção da UNB dos Candangos lá. Estudei matemática na Universidade de Brasília. Muito obrigado. Parabéns à Universidade de Brasília e aos organizadores. Muito obrigado, senhorita Jaqueline Mesquita. Muito obrigado. Fernando Cortez, saluda a todos vocês. Muito obrigado.
Obrigada.
Sandra, deixa eu só, na pergunta do Gilmar, eu queria fazer uma colocação, assim, como eu falei, assim, eu não sei muito do retardo, né, com as EDPs, mas, assim, nessa parte de discretização, eu fiz até um trabalho em colaboração, né, com o Pedro Bila, com o Cláudio Cuevas e um colega meu que é da área da engenharia. E a nossa ideia era justamente, assim, a gente tinha uma EDP elíptica, e aí a nossa ideia, a gente usou, né, soluções radiais, chegou num problema de segunda ordem, e aí a gente fez o seguinte, a gente queria ter aproximações dessa solução, e a gente usou a teoria de escalas temporais. Então, a gente reformulou esse problema usando escalas temporais, e aí a gente usou, por exemplo, a escala HZ, e aí com isso a gente fez várias simulações de tentar aproximar, de fazer estudos como se comportava a solução, se existia solução positiva. Então, foi um estudo bem nessa direção, mas não envolvia retardo, mas envolvia as escalas temporais, e a gente fazia essas convergências, a gente ia de uma escala para outra, convergindo, e via se as soluções também convergiam do problema, em que condições, e fazia algumas simulações para tentar entender o que acontecia no caso da solução da reta, né?
Interessante, bacana.
Legal.
Alguém quer falar mais? Alguma pergunta mais para a Jaqueline? Quem quiser pode abrir seu microfone. Não? Não, parece que não. Terem mais perguntas. Então...
Sí, estoy acá, estoy aquí. Soy
Roxana. Rosana, que é epidemiologista, que é da Matemática.
Muy interesante porque yo trabajo con ecuaciones diferenciales con retardo justamente por esos comportamientos caóticos que existen en este tipo de enfermedades, por ejemplo, con la cuarentena y con todo lo demás. Entonces, justamente lo que decía a propósito de darle esa dinámica es que trabajamos con las ecuaciones diferenciales con retardo, ya sea en la toma de decisión para cuarentenarse, no cuarentenarse, ¿no? Cómo se van tomando diferentes actitudes y en los procesos en general, ¿no? También en lo último que se usa, que es lo que he estado trabajando, es en las noticias, por ejemplo, cómo llegan esos índices de información sobre ya sea las vacunas o ya sea si nos hace bien o mal las cuarentenas largas o cortas. Entonces, todo eso provoca comportamientos de ese tipo que las ecuaciones diferenciales con retardo apoyan muchísimo. Así que me encantó esta plática, Jaqueline, y ya conversaremos más adelante acerca de algunas cosas. Interesante.
Muy bueno. Sí, por supuesto, sim.
Olha, já temos um contato, com certeza, né? Rosana que está aí nessa área aí bastante já, muito bom. Então, a gente agradece, Jaqueline, mais uma vez aqui. Jaqueline faz parte do grupo também, está lá no nosso WhatsApp do grupo, né? Quem quiser mandar algum recado para ela, né? E muito obrigada ao Max, a toda a audiência, ao Marcelo, né? A professora que teve aqui, a Irena Laskaia, e a Lazieca, e a todos os colegas. Muito obrigada, Jaqueline.
Obrigada, Sandra. Eu também queria agradecer aí o convite. Para mim é um grande prazer, né, estar aqui. Também ver tantos colegas aí hoje. Então, muito obrigada pelo convite.